we have the pleasure of Joe Sinkowitz from NOAA and Bob Anderson from the United States Power Squadron. So with no further ado, I am going to change the presenter to Joe, and Joe is going to get started.
Thanks, Randy.
Hold on.
Go ahead if you could.
Hold on one second. I'm switching it over to you now.
Okay.
And you have the con.
Okay. I have several windows up on top of mine. I don't think it's done.
Yeah. And then you need to click on Show My Screen. And screen share.
That window hasn't come up. Like frozen. It may appear that I'm frozen, which would be a shame. Yeah, I'm getting a go-to not responding.
Oh.
Yes.
Do you want to log back in?
No, because I know it took a while. Let me see if it just seems to be catching up at this point. Unfortunately, my travel. You're the presenter. Okay, so I have that. It has not come up yet with it's my screen.
So you have acknowledged that you're the presenter, correct?
I believe so. Yes. Can you see me?
Not yet. I see the marine weather forecasting and your picture and Bob's.
Okay. So I'm not so sure I actually am the presenter. You can see your screen here. How about now?
Yep, there it is. It's up.
Okay. Excellent. Good. Oh, I feel so much better now. So it's my pleasure to participate in this session, marine weather forecasting. Through modern miracles, the three of us that are working on this, I'm actually in St. John's, Newfoundland tonight. Bob is in Seattle area, and Randy, facilitator, is in Fort Lauderdale. So things are actually quite different than they've been in the past. So let me go ahead and get started. Come on, computer. I apologize, my computer is a little bit on the slow side. So, Power Squadron, thank you for the effort. There's a couple of, on slide 2, there's a couple of, an article that Lee Chesno and I wrote some years ago and then rewrote as a reference, the 500 millibar chart. There's also a variety of different content here from weather pages from the Weather Service, and also the last one is webinars instructors are myself. I'm the chief of the Ocean Applications Branch with the NOAA Ocean Prediction Center in College Park, Maryland, and Bob Anderson, who's with the Marine Environmental Committee with the Power Squadron. So it's our pleasure to participate in this tonight. So before we begin, this will be available. It's going to be recorded, and it can be over the next 6 weeks. It can be for those who are registered, can be watched, viewed at your own leisure, and please feel we'll be monitoring the boxes on the right-hand side. So if you have questions, please use the question box. And type in your questions, and we will try and answer at the end of the seminar. So this is the materials, again, Mariner's Guide to the 500 millibar chart, and which is available at that link. And then marine weather forecasting, which is in format for gridded information, numerical forecast models are in best, the standard is basically what we call now GRIB 2, GRIB version 2, and we'll also talk about Weather Service marine forecasts. So let's go ahead and start the review of surface maps and winds.
It should, but...
So So the things that we're going to talk about are the following features: highs, high pressure; lows, low pressure; troughs and ridges, which are axes of both low and high pressure; fronts; and isobars. So these are the typical symbols that are used to delineate pressure features on surface analysis charts. So a high is sinking air, particularly air is converging aloft, and is descending. It's drying as it's descending, so it's associated with clear skies. A low is rising air. Rising air is cooling. As it cools, it condenses, and as it condenses, it makes cloud and then makes precipitation. So a low you should think of as with bad weather, if you consider rain to be bad. I know some people don't anymore, especially in California, and I take that seriously. I'm glad this front is moving in. Trough is actually a area of air density difference. It's not quite the same as a front, but in essence, that's what it is. I always kind of think of it as a front wannabe. A trough axis is basically an area of lower pressure where there typically is a temperature difference, but it's not strong enough to be considered to be a front. The funnel symbols that we use are the red here with the pips facing in the direction of the funnel movement. So this is a warm front. It will be cooler air to the north and the warm air to the south of the funnel boundary. A cold front has it's typically blue, has the triangles, and the triangles also face in the direction of movement. Not all fronts move, so we have to have a delineation for stationary fronts, stationary or quasi-stationary. It's not moving much, we'll consider it to be stationary. And that has a mix of delineation of both cold and a warm front. And a stationary front can become a cold front, stationary front can transition into a warm front. An occluded front is sort of a combination of the two. They're typically found in and around a low pressure center, and they extend from the merger of both the cold front and the warm front. In essence, what they look like is a combination of both, is that they're in reality kind of an extension of the warm front till they wrap around the low center and then they become a cold front. So they're a little bit of both. So let's go ahead to the next slide. So isobars are lines of equal pressure. Basically, the sea level pressure or surface pressure is a reflection of all the three-dimensional structure of the atmosphere. It really is a reflection of both the motions in the atmosphere, but also the temperature density of the atmosphere, which is the main contributor in its temperature. So in essence, you get a two-dimensional view of what is going on aloft in the atmosphere. As a reference, the average pressure on the Earth's surface, sea level pressure, is 1,013.8 millibars. So I mention that because it gives you an anchor or a reference as to whether a low is particularly strong. If it's, say, 1,000 millibars, that's only 13 millibars lower than average. That's fairly typical for a moderate to low pressure system. If a low pressure system is 980 millibars, then that's significantly lower than 1013.8 millibars. And same with a high. If a high is 1025 millibars, that's typically average. I've seen highs as strong as 1080 millibars or even a little bit stronger, and that's with a major Arctic outbreak in Alaska. So it kind of gives you a benchmark. In essence, it's not the low pressure value or the high pressure value. It's really the difference between the highs and the lows. For instance, this low over southwest Minnesota to the high in New England. That difference in there is what is significant, and the greater that difference over a smaller distance, that basically is what generates wind. So the pressure relates directly to the wind at the surface, and we'll go through a bit of that. Okay, so this is the type of graphic analysis that's available on the Ocean Prediction Center website for the North Pacific. This is actually several years old, but today's doesn't look much different than that, except for the big storm system isn't out way to the west of the date line. It's actually just off the Washington coast. So in this example, the yellow lines are the isobars. The lows are delineated with an L with an X, and that low that is here out to the west over the North Pacific along the Aleutian chain is 952 millibars. We use it, the fronts are delineated in color. So this is the occluded front in purple, extending down to the cold front, which comes down here way to the southwest. And this is a warm front that's, so we call it a kind of a stubby warm front that's pushing along in advance of the funnel system up over the Aleutians. We list our warnings with the with each storm system. This one is very intense. This is a winter storm system of hurricane force intensity. So warning categories are gale, storm, and hurricane force. And we have one of those each on this. So we have a gale here off of Point Concepcion. There's a storm north of the Hawaiian Islands. You could almost consider this to be a Kona low. And then we have the big hurricane force cyclone up over the western Aleutians chain. And the isobars give you a good idea as to where they spread apart is where the winds would be weakening, where they're very, very tight, say in here in advance of the cold front, or to the south of the low, south of the occluded front, where we have hurricane force labeled. That's fairly typical for the evolution of a storm system. You get an idea of the character of lows and highs. So let's look at the big storm system here, and you can see how tight the isobars are around the system. 952, compare that to 1013. That's significantly lower. And then look at this high that's here to the northwest of the Hawaiian Islands. 1027 millibar is the high, not particularly strong, but still compared to the 952 low, there's a pretty good difference between the two. The highs are much more open. The pressure gradient, or the difference in pressure, is much more relaxed. They're more amorphous than a low, which can be very, very tight circulation. But just to give you a contrast, if you're a sailor, then obviously the low has very, very strong winds with it, and the high here, and in fact all along in this area here, from this ridge all the way down to the southwest. So this is a sort of a ridge of higher pressure where the isobars change direction. So this is higher in here, all the way down to the high and extending down to the southwest. Those would be areas of relatively weak winds. So let's go ahead to the next slide. So the pressure gradient force, the difference in pressure, is what causes the air to move from high to low pressure. The greater the difference, the closer the isobars, the faster the wind speed. Friction slows down the wind, even over the ocean, this friction, and turns the low-level winds near the surface. It turns them sort of across the isobars a little bit. Probably of these, the second most important is that because we're on a rotating Earth, there's something called the Coriolis effect. And it's a function of latitude. The higher the latitude, the more curvature, the more the Coriolis effect has an impact. And what it does is it actually causes the wind to curve to the right in the northern hemisphere and to the left in the southern hemisphere. Without the fact that we're on a rotating Earth, without the Coriolis effect, basically highs would fill lows, and then pressure would be 10, 13 millibars everywhere. But because of the Coriolis effect and the added effect of friction, highs and lows become circulations. With a high, the wind flowing descending and then flowing outward, and with the low, the wind ascending or flowing inward. The Coriolis is 0 at the equator, and it also is a function. It increases with wind speed, so the force actually is a function of the wind speed too. Okay, so surface wind flow. So, as I said, flow from high to low pressure due to the pressure gradient force. So highs would fill lows, all the air would fill into the low, and then everything would equal out. But because we're on a rotating Earth, the winds curve to the right in the northern hemisphere due to the Coriolis, and they flow at an angle across the isobars. Over land, there's a lot more friction, so that angle can be as high as 45, sometimes even 50 degrees. Over the water, it's around, 20, 25 degrees, 20 degrees. So from a high, the wind actually blows outward, so think of it that way, outward across the isobars towards lower pressure. And in a low, inward towards lower pressure across the isobars at about 20, 25 degrees. And that can change depending on the structure of the atmosphere and whether or not there's cold air flowing or warm air flowing. And depending on whether or not the atmosphere is stable or unstable, whether it's mixing vertically. Okay, so this kind of repeats what I've said and gives a little bit more of a relative sense. If you're passing to the south of a high from the east, then your wind would be from the northwest. As you get closer to the south of the high, the wind would swing around to north and then to northeast. And then as you keep going, the wind would come more aft and to the east, and then eventually perhaps to the southeast. So same sort of transit except for with a low, then you would start out with a southeasterly. As you transit to the south of the low, the wind would come around to the south, more on the nose. And as you keep going, you actually would come through the eye of the wind, and the wind would come from your port bow onto your starboard bow and eventually onto your starboard beam. So you would start out with southeasterly all the way to northwesterly as you pass south of a low. If you pass north of a low, then you'll encounter basically the wind coming around the other way. So again, reiterating, close to the isobars, the higher the wind speed. The isobars wind flows across the isobars at about a 20-25 degree angle over the open ocean, spiraling inward in a low and spiraling outward in a high. Okay, so this also gives you an idea of sort of similar. It's 15 degrees over water. That's probably, I kind of like using around 20 just as a rule of thumb. And again, it's a little bit more over land, 30 to maybe even 40 degrees to 45 degrees, depending on the regime, across the isobars. The source that's listed here is from two European satellites called ASCAT. MEDOP is the satellite, the instrument is called ASCAT, and this link will take you to basically the current sampling from this satellite, where it actually is a radar and samples the ocean surface and can give you an estimate of the wind speed and the direction. A very, very accurate, very high resolution. It's 12.5 kilometer resolution between spaces in the sampling. It's actually, if you have time tonight, take a look at it, because you can go see the storm off the west coast. In fact, that information should be relatively fresh now. So let me go ahead to the next. Okay, so we've talked about the surface, but there's a lot more to the atmosphere than that. So I want to go over a little bit about upper air winds and charts. So surface winds vary in direction. The wind, the southwest, west to northwest direction dominates, but depends on where you are. If you're in the trades, then it's northeasterly. Have more rotary patterns with the lows, into the lows and out of the highs. And aloft, as you get away from the surface and get away from the friction of the surface, the wind tends to be more of a west to east flow. Thus we have the term the westerlies. Weather systems tend to move from west to east in a general sense, and we'll talk a little bit about that when it doesn't happen as we look at 500 millibars. The flow is smoother. It's less impacted by friction and tends to be more in streams. The flow does sweep around highs and lows as it does on the surface, but not as sharp an angle. It actually tends to rotate more around them. And the wind speeds are higher. You're away from the friction. The pressure gradient force increases with altitude, and the upper level winds are more representative of the weather pattern. So kind of gives you the answer if you're able to use upper level winds such as the 500 millibar that we'll talk about, then it gives you a better idea as to why a storm system is behaving the way that it's behaving, why it's tracking the way that it's tracking. So let's go to the next. Okay, so this is a surface map. This is from a few years ago over North America, and we have a weather system up over to the north of the Great Lakes, south of Hudson Bay, and with a front trailing off to the southwest, and another low over Texas-Oklahoma border. And there's a low coming into the Pacific Northwest with a stationary front draped across British Columbia and down across the Rockies and down to the southeast. So let's go ahead and look forward. And this is the upper level chart. This is the 500 millibar, which we'll talk in more detail. But the flow or the winds blow relatively parallel to these contours. These are height contours. They're not pressure values. The pressure is constant across the 500 millibar chart. Rather than height these are contours of height. So the height varies based on the density of the atmosphere, and the atmosphere is more dense, which means the heights are lower in a colder atmosphere than it is in a warmer atmosphere. So the heights tend to be higher to the south and lower to the north, where the air is colder. And where you have these pockets of colder air, that's where you have the low heights, and they're also associated with weather systems. So in this case, the higher heights are over the southern tier of the United States, along the Gulf Coast, with high values over the Gulf of Mexico, and the lowest are out over the North Atlantic, east of where I am right now, up over north of the Great Lakes, and then again off of Vancouver Island, and with another area of interest well to the south, to the west of California. Now, the flow aloft, basically where you have the height contours coming together, you have what we call confluence. The mathematical definition is, well, confluent basically means that the flow is actually increasing that area. What it means is that the air is coming together, and it has to go somewhere. So in an area of confluence, you typically have sinking motion. In an area of difluence, which is to the east in the red box, where the height contours are spreading out instead of coming together, then that's an area where you have upward motion, basically, because the air is spreading out, something has to replace it. So the air that replaces it is from below, and that comes up. So think of on the east side of a trough, and this would be a trough where there's an area of lower heights, an axis of heights, right in here. The way you have the difluence is, actually somebody has a dog barking. It's not a Newfoundland dog. So the difluence here basically is with this upward vertical motion. That's where you expect clouds. That's where you would expect not just clouds, but also where you'd expect precipitation. And you'd expect higher pressure at the surface where you have the confluence. Okay, and that is indeed, the funnel system lies underneath the area of the difluence, and the high pressure with a slack pressure gradient and a high down here in southern Oklahoma to Kansas is where the confluence is. So things are connected. They happen for reasons, and unfortunately the weather repeats in some way, shape, or form. So we over the years have learned how the behavior is. Okay. So the 500 millibar is a constant pressure surface aloft. The topography of the pressure surface, again, relates, this reiterates what I just said, it relates to the temperature structure below the pressure surface. So at 500 millibars, about 18,000 feet in the atmosphere, then it goes, the height of 500 millibars is higher where it's warmer in the column, and where it is colder, more dense, then it is lower. And so when you see highs and lows aloft, they're at 500 millibars, they're actually higher heights and lower heights. They're not higher pressure and lower pressure. Okay. So again, the topography of height contours, this similar, we had a similar diagram for the sea level pressure, and here is a trough, and that actually you can see it sort of extends all the way up to the north of into the Canadian archipelago. There's another trough of lower heights, what we would call a full latitude trough. It's a fairly extends quite northward and southward in the height field off the west coast. This is a ridge axis along the west coast from, if you follow the spine down through the Northwest Territories all the way down through British Columbia and actually down all the way to Baja. That's a axis of higher heights. That's a ridge, and there's sort of a broad ridge here out off the Atlantic coast in advance of the trough. And typically the way things work is you have, trough, ridge, higher heights, lower heights, and this is all in motion and moving, and we'll see some of that in a bit. Okay. This is actually out of the 500 millibar article. This is actually a slight slice of the pressure values or the heights with the thick line is the 500 millibar height. And this was actually an example from December of 2005. And even though it's relatively subtle, you can see that there's a dip right in here up over the east coast of the United States. There's a low at the surface, and these are actually, this is the trough from the surface extending upward, and then in here is the basically the temperature trough that goes along with that. So here's where the temperature lines drop and then kink upward. So this is the trough that tilts with height with a low pressure system, and we'll talk more about that, the relationship between the surface and the upper level. So the pressure trough, the pressure trough is the red, and the temperature trough, which lags behind it, is in the blue. So you get an idea as how the structure works. Okay, and this is a similar slice, but looking back towards the east coast of the same time and same weather system. So we have a low that's just off of Massachusetts, off of Maine, and this slice right in here is the height of the 500 millibar level. So you can see that it actually lowers as you go farther north. The pressure trough, height trough is back here, pressure trough is down here on the surface. Okay, so there are different upper level charts. There's a 200 and 300 millibar chart. Respectively, 200 millibar is about 39,000 feet up on the where aircraft fly, and 300 millibar is about 29,000 feet, and that's about where the polar jet stream is. The 500 millibar chart is actually below the jet stream. Typically, unless it's an extremely cold atmosphere, you actually can get a jet to be reflected at 500 millibars. It averages around 18,000 feet. It's a very powerful surface weather prediction tool. It represents the upper level steering winds. Vorticity is a term that we like to use, but it really is spin in the atmosphere. If you put a paddle wheel in the atmosphere in order to see how it would react in the flow. If it would spin one way, then that's associated with rising air. If it spins the other way, then that's an area where the air is sinking. And the trough and ridge patterns evolve over time. The energy that we describe associated with weather systems are basically associated with troughs and the ridges, and I'll show you some of that. Lower down, 700 millibars, about 10,000 feet, 850 millibars, about 5,000 feet. This is where a lot of the near-surface features, the fronts exist. It's where temperature and moisture advection is concentrated, where the movement of moisture and temperature occurs. And at 700 millibars, that's a good level, about 10,000 feet, for the steering level for air mass thunderstorms. Bigger thunderstorms may actually be a little bit higher than that. And actually, they can actually move in a little bit higher than that. Okay, so let's hone in on the 500 millibar chart. Okay, so again, the average height is about 5,600 meters or 18,000 feet. Can range near the poles, 4,700 meters. If those of you who are in the East Coast or in the Midwest, the polar vortex, basically that would have been that is a low heights associated with 500 millibar height. That's typically what we use, and it may have been around 5,100 meters or so, and it can be as high as 6,000 meters near the equator. The contour lines, the higher the height, the higher the pressure. The way that they're labeled, if you add a 0, you'll get the altitude in meters. The closer the contours, the faster the wind. And the winds flow mostly parallel to the contour lines. We have a fancy word for that called geostrophic, but that's something you don't need to know. The important thing is that you know that the winds blow nearly parallel because there's very limited friction to the contour line. So you get a good estimate when you see the 500 millibar contours as to what the flow is doing. The closer together they are, the higher the wind speed. The wind barbs show both the direction and speed. I'll show you those in a little bit, and the patterns are used to predict the surface weather, and they're related, surface weather and the 500 millibar. Okay, so this is the same surface analysis I showed you earlier. The big storm system over the Aleutians, the one to the northwest of Hawaii, and we had the little gale area off of the California coast with sort of the seasonal high pressure. And several lows up in the one in the western Gulf of Alaska and the other one in the eastern Bering. So let's go ahead and look at what the 500 is for the same time. So remember I said 4,700 is about the lowest. So that's a very intense low. This is 492 decameters or 4,920 meters is the height, the low height over that storm system. There's a ridge axis that tends to be difluent. Lo and behold, over if you see the clouds that are in behind or underneath, where you have the difluence, that's where you have cloud, because that's where you have upward vertical motion. You can see that all the way along as you trace to the west of this zigzag line, still underneath the ridge. The storm system north of Hawaii, 5,600 meters is the height of that, certainly higher than the 492 up over the Aleutians. It's farther south. The air isn't as cold. And you have an idea that, again, I showed you how the heights are spreading, and that's where the cloud is, out to the east, where the heights spread apart. Where they converge, like say farther to the east, you have much less in the way of cloud, and that's certainly true to the northwest of this system that's north of Hawaii, right in here, where the air is converging or is confluent. You have relatively clear skies, and where it's difluent, you'll see that it's cloudy. There's a little feature in here, we call that a trough. That's this dashed line, and to the east of that trough, it's a little bit difluent, and lo and behold, there's a cloud there. There's another trough here to the east in this kind of area of southwesterly flow, and you can see again that the clouds align to the east of that trough axis as the trough is moving along, where the height contours are spreading out. It's subtle, but they're spreading out a little bit there. So relates to the surface, you have features aloft that are reflected on the surface and vice versa. The tough one is off of California. That basically is a near surface-based feature with those strong winds. That's because it's so warm in interior California, and the ocean is relatively cool, that you actually get a relatively local area, low pressure, and you get a strong northwesterly flow. For anybody who's from the West Coast, you know that Cape Mendocino, Cape Blanco, Point Concepcion, it tends to be breezy there. So the winds that are on here, it gives you a good idea. Let's start back here over northern Japan. This is an area, you can see that the flow is the lines are very close together, and there's an axis in here. Let's start right here to the east of where Tokyo is, And that's 1 flag and 1, 2, 3, so that's 80 knots of wind near parallel to the height contours, 95 knots just farther to the east. We keep going eastward and you have 90 knots. There's actually right in here where the height contours are very tight together, there's 105 knots of wind at 500 millibars, so it's blowing pretty hard. It's not as strong as a jet stream. I've seen up to 230 knots in this area out on the Pacific, but still that's something to be respectful of. That gives you an idea that if something's embedded in that, it's going to move. Okay, so, and we tend to plot on here anything that's higher than 35 knots. So this is a little bit vacant in the summertime, but 105, 110 knots is a pretty high value for the typical over the North Pacific, especially in the month of December when this was. Okay, so on that chart, and all the height contours are a single thickness except for one, and that one is the 564 decameter line, or the 564 line, or 5640 meters height contour. And it's usually shown, we do it as a thicker line, whether it's black and white or whether it's in color. It's a good indication of the surface storm track. It usually lies between 300 to 600 nautical miles to the north of that, and it parallels the height contour. It's a good indication of the flow. Worst weather, meaning highest winds and seas, are to the north, typically to the north of the 564 line. They're strongest in the cold air, in the west quadrants of the mid-latitude systems, like we saw with the one over the oceans. And it usually marks in summertime the southern extent of 30 knots and 35 knots in the winter. If you were doing a transatlantic, a good rule of thumb is to use the 564 line as your northern, the northern point that you want to go in order to try and avoid the nasty westerlies and to avoid the most significant storm systems. It's a fairly typical routing exercise when people are transiting going from west to east. Okay, so as an example of that, this is a North Atlantic case. So in this case, not only a thicker line, but it's actually a different color. It's more of a reddish color. So this is the 564 line coming off the Virginia coast and extending east-northeast to sort of a broad ridge over the eastern Atlantic, and then dropping down in west-northwesterly to northwesterly flow across Portugal and Spain into North Africa. So underneath this are color-coded winds that were derived from a satellite from Quickscat way back in before it failed in 2009. The yellow and the dark green arrows are winds of 30 knots and 35 knots. So his westerlies in here, and you see the strength of the winds from the 500 millibar up above. So pretty good indication in this case that, yeah, the 564 actually matches pretty well with the southern extent of the gale force winds. And this is actually a March case, so this would that would be continuing to be considered winter. And similarly here in the northwesterly flow off of Iberian Peninsula, the Bay of Biscay, you have northwesterly at the surface of 35 knots or higher. And again, the 564 line is the southern boundary of that. To the south of the Azores, there's a large area of higher heights, and the surface winds are relatively light with that area of high pressure. The surface high would be just right under this 583 high height. So let me go on. Next. Okay, so I want to talk a bit about the 500 millibar patterns, long waves, short waves. We've already seen some short waves with some of the cloud structures that I was showing you, short wave troughs and surface lows. And we're going to talk about different flow regimes, zonal flow, meridional flow, what a blocking ridge is, and what a cutoff low, what they are, because on the slide I have, I think it has 3 of them on it. We'll go ahead and look at long waves. So 564 line is the thick one. You can see kind of looks like spaghetti there, but it's not crossing. That is looking down on top of the pole in the northern hemisphere at the 500 millibar height contours. And you can see how, if you follow the 564 line around, you see how it undulates. For instance, as you come into the west coast, the flow is southwesterly. It reaches a ridge, crests over the Rockies, and then a trough drops down in the Tennessee Valley, Mississippi Valley, and then the heights rise again as you come off the Canadian Maritimes and then across the Atlantic. So in the larger scale pattern, what we call long waves, are the long-lived features that are associated with the weather pattern. This area extending over Eastern Asia into the Central Pacific, that would be considered to be a long wave trough. Smaller scale troughs rotate through that trough, through the longer wave trough. So what we call them short waves, and they tend to be associated with specific weather systems or storm systems. I'll give you an example. That is a shortwave trough here. It's relatively subtle. North of Hawaii, south of the southwest Alaska Panhandle. That's a shortwave trough in there. More than likely, there's a weather system, a low pressure system somewhere out here into the east. There's another trough that's approaching the west coast. That's more than likely a shortwave trough. This may be a little bit subtle, but there's a little bit of this ridge is so broad that may actually be a long wave ridge, a relatively permanent, semi-permanent feature. It might last for 10 days or so over the western U.S. It looks like there is some sort of trough. There's a sharp trough that's rotating through the eastern United States and the anchored in the Tennessee Valley, swinging eastward. That feature, just by the shape of that, would be migrating eastward and northeastward. Another broad feature, this is an area of higher heights. Actually, I guess that is a low. I'm looking at it sideways. There's a broad ridge extending across the Atlantic, and underneath that ridge is a area of low pressure or lower heights. So there's some sort of feature closed off low off Africa, and there's a deep trough over Central and Eastern Asia that's a long wave trough. So the short wave troughs are associated with the weather systems, and the longer waves are more indicative of the weather pattern, the persistence of the pattern. Okay. So let's see if this is actually going to work. I have a loop here. This is sort of a stutter step along. I think I'm at the high end of the performance of that computer. And this is actually a fourth loop. It's actually jumping a little bit. I apologize for that. The idea here, to give you an idea, is to how the shortwave troughs move from west to east, encircling the pole, basically, across the northern hemisphere. This is the westerlies. Is what you're seeing is where the contours are, the westerlies. So in the 40, 50, 60 knots, some even a little bit faster than that, and they're embedded in the flow. So they can enhance the long wave pattern. They can actually decrease the long wave pattern. They can actually work both ways. They can amplify or the short waves, or they can actually de-amplify the pattern. So this loop is going to work very well for you. So I'm going to go ahead and move on to the loops. There we go. Okay. So this here is 1001 surface low. This is, again, I apologize, it's a winter case. This is a February case. So this is the height contours associated with 500 millibar pattern. The flow is from west to east. It's near zonal is what we would call it. It's moving basically a little bit across the parallels, but not that much across the parallels. You can see where the high cloud ends in here off the east coast, and that's where basically the trough axis is. So that's the shortwave trough. It lags behind the surface low when it's developing. As the low develops, it actually will catch up to the low, and then you'll actually see that at 500 millibars, the circulation actually grows up to 500 millibars and even higher. So let me go ahead to the next one and see if this actually works. So this should be a loop. Hope it works. I'll let it go a couple of times. So this is a rather extreme storm, and kind of gives you an idea as to how it develops. Unfortunately, my system is lagging. So I don't know if it's actually going to fill in. I'll let it do this for a little bit. So you get to see the kinks as they move out and how it actually encircles over time. Maybe what we can do is make this slide available so that people can download it, because it works fine if you are trying to view it. This is a very, very stormy period over time, and the satellite imagery and having the height contours of the 500 millibar with the surface pressure values, that's what's on here in red. It gives you a pretty good idea of the relationship as to how a storm system evolves over time. So let me go ahead. It's not gonna even out over time. Sometimes they do. Let me go ahead to the slide. Okay. So this is an example. There's two slides like this, and these are examples basically of the evolution of storm systems. So the idea on the bottom panel is for you to see the relationship of the trough, the lower heights aloft, the lower pressure at the surface, how it tilts with height through the evolution of the storm. So it tilts back to the northwest with the upper level trough lagging behind the surface, because the low is actually under that area of diffluence where the height contours are spreading out. With time, what you'll see here is that the trough will actually catch up and become more vertically aligned with the surface feature. So the feature that we're looking at here is actually this one back to the west over the lower Mississippi Valley. These are in 12-hour time steps. So the feature is coming off the coast. There's a surface low here. These are surface. These are 500. And in the third panel, the trough is actually moving off the coast. There is still some tilt with it. The surface low is out in here, 500 millibar. So it does tilt. Let me go ahead to the next one. And